Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a pleasure to introduce Minlan Yu from Princeton. She graduated just 5 years back from Peking University in China, so she is straight out from grad school. Minlan has interned in the past with us, with Albert, Dave, and Lihua in Bing. She has built a measurement infrastructure that allowed her to look at TCP level stats and collect a fair amount of network and host integrated measurements that led to discovering TCP anomalies. In the same vein, she's done a bunch of work, and she's best known perhaps for doing cute algorithms that in routers and switches that do that enable better measurement, better access control policies, that kind of stuff. All right, I'll let her start.
Thank you for the introduction. It's my great pleasure to give the talk here. And the talk is about edge networks, those networks in companies, campuses, data centers, and home. So recently there have been growing interest on these edge networks, but mostly people focus on how to make these networks bigger, faster, and more efficient. And what I'm going to focus today is on the management of these edge networks. Based on Yankees Group's report, in most enterprises today, network management takes about 80% of the IT budget, but are still responsible for more than 60% of the outages. So this management is an important topic, but it's underexplored for these data centers and enterprise network area. In this kind of networks, ideally we hope to have the users and applications of first priority and only make the network as a secondary. So we want to make the network as transparent as the air we breathe, so that it can be totally support different diversity of applications and different requirements from users. But of course, today's networks are far from this goal. So instead of working on how to make today's networks easier to manage, we focus on how to redesign these networks so that it's easier and cheaper to manage. There are three challenges to manage these edge networks. The first challenge is these networks are growing larger and larger every day with lots of hosts, switches, and applications. On the other hand, people hope to enforce a lot of flexible policies for different management tasks like routing, security, and management. Finally, we only have simple switches in hand. These switches have constraints on cost and energy. But how do we use these simple switches to support both large networks and flexible policies? In this talk, I'm going to present to you a system that achieves all these three challenges in the same time. First, let's look at two example large networks. The first is these large enterprise networks. In these networks, we usually have hundreds of thousands of hosts, and we have thousands of switches connecting to them. On these hosts, people may run a diversity of applications. These applications may have different traffic metrics and different performance requirements. The data center networks are much larger than those enterprise networks. In data centers, we usually have virtual machines running on these servers. So totally there could be millions of virtual machines. And these virtual machines can move from servers to different other servers. And also we have different layers of switches connecting these servers together. And on these servers, people may run different applications. Yeah, question?
Why does the number of applications matter? If these were like different flows, is that what's going on, or like just the presence of different applications is somehow?
So today, people not only want to manage the switches, the servers, but also the applications. They will want to provide different routing for these applications, different QoS, access control for these applications, or improve the network performance for these applications. So if you have a huge amount of applications, each with different traffic metrics or different performance requirements, it's a challenging problem. And it's like more challenging in the data center than in this enterprise environment, because data centers have more diverse traffic patterns and much higher performance requirements. And in order to support these larger networks as operators today, they also want to enforce flexible policies. Today's network operators have so many considerations. They want to improve network performance, improve security, support host mobility, saves energy, saves cost, and makes the network easier to debug and maintain. So in order to achieve all these management goals, operators usually have different kinds of policies. The first example of policy is these operators may want to provide customized routing for different applications. For example, provide like shorter latency paths for those real-time applications. They may also want to enforce access control rules in the switches to block the traffic from malicious users. Finally, for counting and measurement, they may want to measure the amount of traffic from different users and different applications. But on the other hand, we only have simple switches. Today's switches usually have increasing link speed. Today's data centers usually have 40 Gbps link and even more. So that means we can only process each packet with tens of nanoseconds. In order to process these packets with fast speed, we can only run this very small on-chip memory. This memory is very different from the memory we have in our laptop because they are very expensive and power hungry, and as a result, we can only afford to have a small size of it. But on the other hand, operators want to support to store lots of state in this small memory. Just to support forwarding rules, we may have millions of virtual machines at data centers. That means we may need to install one forwarding rule for each host or each switch in a small memory that could consume a lot of memory. And at the same time, we also need to use this memory to enforce access control rules, quality of service for different applications and users. Finally, we may want to maintain different counters for specific flows. It also requires memory. So how can we address this challenge of using this small memory to store this large amount of data? We built a system to manage these edge networks. In this system, the operators first specify the policies in the management system. And then this management system will configure these devices, both the switches and end hosts, to express these policies. This management system will also collect measurement data from the network to understand the network conditions. So we built two systems. The first system works on the switches. It basically focuses on how to enforce flexible policies on the switches. And the second system is called SNAP. It focuses on the upward direction, how to scalably diagnose performance problems on the end host. So a common approach I take in both DeFi and SNAP work and many of my other works is that I want to first identify those practically challenging problems. And then I want to design new algorithms and data structures. For example, in defense work, I provide new data structures that can make effective use of the switch memory. And in SNAP work, we provide new efficient data connection and data analysis algorithms. And these algorithms and data structures wouldn't be enough if we can't validate them with real prototyping. So in defense work, we actually build prototypes with OpenFlow switches. And in SNAP work, we build prototypes with both Windows and Linux operating systems. Finally, we hope to really make real-world impact with these prototypes, so we actually collaborate with industry. For defense work, we collaborate with the AT&T and try to evaluate our prototype using its network configuration data. And for SNAP work, we work with the Bing group in Microsoft and have already deployed this tool in this production data center in Bing. So first, let me talk about DeFi. DeFi's basic problem is how do we scalably enforce flexible policies on the switches? So if we look at traditional network, when we buy a switch, we usually buy two bundled functions together. The data plane, which is the hardware part of the switches, that actually forward the packet. The control plane, which are the brains in these switches, that run some protocols to decide where the traffic should go. Since these two parts are bundled together in the switches, in the data plane, they are both limited. For example, in the data plane, different vendors may provide different hardware, and they only support limited amount of policies. And in the control plane, since it's already designed when we buy the switch, it's very hard to manage and to configure. So in order to manage traditional network, today operators only manage the network in an offline fashion, and sometimes they even go through each switches independently and try to manually configure them. So in order to improve the management of these traditional networks, there have been two new trends. The first trend is in the data plane. We call it flow-based switches to support more flexible policies. And the second trend is in the control plane. We have this logically centralized controller to make management easier. I'll talk about these two new trends in more details. The first trend is the flow-based switches called OpenFlow switches. These switches have already been implemented by different vendors like HP and NEC, and it's already been deployed by different campus and enterprise networks. So what these switches does is it basically performs some simple actions based on the rules. The rules are basically matching on certain bits in the packet header, and the actions could be draw packets from a malicious user, forward the packet to a particular port, or count the packets that belongs to the web traffic. So all these rules can be represented in this flow space I draw here. This flow space here, I'm showing two-dimensional flow space. The x-axis is the source and y-axis is the destination. So here, this red horizontal rule shows that I want to block traffic to a particular destination, and this blue one shows that I want to count packets from a particular source. And in real switches, these wildcard rules are stored in a specific memory called TCAM. There are two features of TCAM. The first feature is TCAM supports wildcards. For example, the first rule here shows that X can be wildcards and Y should be exact value 1. And it describes this red rule here. And the second feature of TCAM is it has different priorities. So if a packet matches multiple rules in TCAM, only the rule with the highest priority will take effect. And in today's switches, there are only limited amount of TCAM because TCAM is on chip and it's very power hungry. So it's very important for us to reduce the amount of rules we store in this TCAM memory. And the second trend is that we want to have logically centralized control plane to make management easier. So now we have this big centralized brain that operators can easily configure their policies in a central place. And then this brain takes the job of deploying policies of all the switches. This makes management easier, but it's not scalable. And if the controller is out of its fields, then the whole network may be out of control. So in order to solve this problem, we present defang. It's a scalable way to enforce fine-grained policies in the switches. Defang's idea is basically you pull back some lower stem function of the brain back to the switches, and by doing that, you can achieve better scalability. So before I talk about how do we enforce policies, we can think of what's the most intuitive way to enforce policies from the brain to the switches. The third solution is that we can just pre-install the rules in the switches. So the controller can pre-install the rules, and when the packet arrives at the switch can match the packets with the rules and proceed it. But the problem here is it doesn't support host mobility. When hosts move to different places, that all the rules that are associated with this particular host need to be installed in all the switches that the host may connect to. And usually, a switch don't have enough TCAM memory to store all the rules in the network. So a different solution that's proposed by Ethan's work, its basic idea is we can install the rules on demand. When the first packet arrives at the switch doesn't have any rules, so it buffers the packet and sends the packet header to the controller. Then the controller will look up its rule database, find out the rules, and install the rules in the switch, so that the following packets can match these rules and get processed. But the problem here is we can see the packets goes an extra long way of going through the controller and come back. And based on our experiment, even when the controller is near the switch and the controller only have a small amount of rules, it still takes about 10 milliseconds to go from the switch through the controller and come back. There are two 10 milliseconds.
Really?
There are two
That's
problems.
really a long time.
Yeah, that's really long. So there are two contributors to this long delay. The first is that the switches. The switch only have very small CPU, so it can't do this kind of buffering and sending in a very fast speed. So it has a lot of delay here. And another delay is from the controller. The controller needs to look up the rules and try to find the rules and install it.
That sounds like a disk I/O latency. Is the controller doing disk
And
I/O?
in our experiment, since we make the controller really simple, most of the 10 millisecond delay comes from the switches.
That comes from the switch.
Yeah.
Wow. Okay.
Yeah. So if the controller getting complex, it will have more time delay. And also we find out it's like hard to implement with today's switches because it increased switch complexity. The switch can't just use first in, first out buffer because it has to buffer the packet while continuing to handle the other packets that can match the rules that are already in the switches. And once it receives some rules from the controller, it has to find a way to retrieve the packet from the buffer. And finally, if there are some malicious users who send traffic to a variety of destinations through a variety of ports, then it can always invalidate the rules in the switches so that it can make all the packets that arrive at the switch experience this extra long delay and also increase the overhead at the controller. So in order to find out a new solution that can address these two problems we've seen with the two approaches, we hope DFIN could, the project we built, can scale with the network growth naturally. It can address the limited TCAM entries in the switches and the limited computing resources at the controller. And also we hope to improve the per packet performance so that we can always keep the packets in the data plane to reduce the delay of each packet. Finally, we hope to have minimal modifications of the switches so that we don't need to change the data plane hardware, and it's easy to deploy the DFIN. And our idea is very simple. We just want to combine this proactive approach and reactive approach together so that we can have better scalability, higher throughput, and lower delay. And DFIN's design has two stages. In the first stage, the controller proactively generates the rules and distributes them to some authority switches. So in our design, we still have a centralized controller. So it's still easy for operators to configure the policies there. And then this controller will represent these rules in the flow space. Then the controller will partition this flow space into multiple parts and assign each part to one authority switch. At the same time, the controller will distribute some partition information to all the switches in the network, so each switch knows how to handle the packet. When the switch receives some packets, it knows which authority switch to ask for the rules. At the second stage, since the rules are already pre-installed in the authority switches, we can use the authority switches to keep the packets always in the data plane, and then reactively cache the rules. So here's how it works. When the first packet arrives at the ingress switch redirects the packets to the authority switch. And then this authority switch can process the packets according to the rules. At the same time, the authority switch will install some cache rules so that the following packets can get processed locally at the ingress switch and directly forwarded. So we can see the key difference here between DFIN and the previous reactive approach is now the packets traverse a slightly longer path in the data plane instead of sending the packets through the slow control plane. So, yeah.
So by default, if you have no policy for the first packet, it automatically redirects to the authority switch.
Yes, so if there's no cache the rules to handle the first packet, then the ingress switch will redirect the packets to the authority switch. Yes.
This is a detailed question. Like, are you doing like MAC in MAC encapsulation here or redirection?
So there are different solutions. The first solution is you can just use IP encapsulation. to do this kind of tunneling from the ingress switch to the authority switch and to the egress switch.
And doing all of that still tends to be faster.
10 milliseconds. She got
Yeah.
a budget.
That's much faster than that. And today the switches don't do this kind of encapsulation in hardware, so we hope to use VLAN tags to improve the performance. Yeah.
So I don't understand something. You said that the reason you had 10 millisecond delay, most of it came from the switch.
That's in our evaluation because we have a really simple controller.
Okay.
Yeah.
So suppose you also had a similar kind of, so you had a switch which was not very, which didn't have very powerful CPU.
Mm-hmm.
Now you're going to ask that switch to do a lot more. You're going to ask it to not just make a query to the central controller, but you're going to ask it to do MAC in MAC or IP in MAC encapsulation
Mm-hmm.
and a rule lookup. And that's going to take less than 10 milliseconds?
So rule lookup is what the switch usually have to do.
Okay.
If it has cache
That's
rules.
fine. So you're saying that
So-
MAC encapsulation takes less time than sending a query to the controller?
That I'm not sure, but based on our software evaluation, it's faster than sending the packet, buffer the packet and sending it to the controller. And we have a solution that uses VLAN tags that can be much faster done in the hardware rather than like full encapsulation to further improve that. But the challenge of using VLAN tags is now the authority switch don't know the ingress switch address anymore. So although we can implement the tunneling with VLAN tags, we can't implement the rule caching scheme with VLAN tags. So instead of doing that, we can move the caching scheme back to the controller.
So the thing that you're improving on top of Ether is just the first packet delay,
Yes.
nothing else.
So basically, the first packet delay, we benefit from moving from software to hardware. And the second better thing we do is this kind of scalability. It's distributed instead of centralized. So it's like scale more with larger networks. So with Ethan's approach, with much larger networks, you no longer can have a centralized controller.
What's the largest network Ether has been deployed?
For now, we're only looking at like the network with thousands of switches. And for that, later in the evaluation, you will see that the one single centralized controller can only process like 50K flows per second. So that means for 1,000
50K new flows per second, right?
new
Because-
flows per second. And for a network with 1,000 switches, then you can only support like 50 new flows per second from each switch.
Okay, but that's a different bottleneck than the 10 millisecond bottleneck.
Yeah, that's a different bottleneck. That it's like more about the throughput bottleneck rather than this delay bottleneck. So I hope defense solution can address both the delay and the throughput bottlenecks.
So how much faster is it then to encapsulate and send it? I mean, how much time does it take?
So based on our software evaluation, we use the software click to implement these kind of buffering techniques. And the encapsulation is the difference is like 10 milliseconds versus 1 millisecond.
So what is the purpose of the encapsulation? Just to know where the packet came from?
The purpose of encapsulation is to create a tunnel from the ingress switch to the authority switch. So all the switches in the middle wouldn't will know how to send the packet and wouldn't do another redirection. Right?
These aren't physical links.
Why is it bad to do another redirection? I mean, the redirection is what happens. It's the switch looked up the packet in its TCAM and saw the default rule said send it that way on that link.
Mm-hmm.
What would be the harm if all the switches did that on the way to the authority switch?
So here, when the packet arrives at the switch knows based on this is the direction the authority switch needs to go. And that means all these switches in the middle should also know that the ingress switch hasn't processed the packet yet and need to redirect it. Right? If the ingress switch already matched the packet with the cached rules, then it can be sent directly. So all the switches in the middle should not do anything. So all the switches in this link need to know that it need to redirect, and all the switches here you should not know. So it's like add to the complexity. And
You could
if
put
you
it
use
in the switch is saying if it's on this VLAN, it will
Yeah,
actually
VLAN tag is
send it to the
basically.
So in terms of the expressivity of the policies that you can have now, this is similar to just dealing with the controller throughput bottleneck using multiple controllers.
Yeah.
But
yes.
if you have multiple controller, where are you going to place it? So do you have like all the packets sent through an actual network to this distributed amount of controller or not? And how do you distribute the state among these multiple controllers? So like one thing I can see is you can use defense technique to distribute the state among these controllers. But if we move these kind of states back to the switches, then you no longer need these kind of actual links to go through the controller.
Okay, so I hear you saying there's a trick to distributing these rules. When you say like you can use defense trick to partition the set of rules along multiple controllers,
Yes.
so that's not something that's straightforward.
Yes, like so we choose to do partition instead of replication. Like a naive solution would be you let all the controllers store the whole set of rules. And so whenever the packet arrives at whichever controller, it can process it. But the problem there is like how do you direct the packet to the right controller, and how does this controller maintain consistent state with other controllers? Yeah.
You're going to tell us what happens if after you partition the rules, let's say the authority switch goes down?
Yeah, I'm going to talk about it. Okay, so in summary, the key benefits we get is like now we move the packet proceeding totally in the hardware path instead of going through the controller path. And also it's distributed among many authority switches. And an extreme example is like if this rule caching action is really slow, then in our design, the packets wouldn't need to wait for the rule caching scheme. So all the falling packets will also get redirected through the authority switches. Okay, so now the question left is, since we have a group of authority switches, how do we know which authority switch, how does the ingress switch knows which authority switch to ask for the rules? So if we look at this example, we partition this flow space into 3 parts, and to describe this partition, we just need 3 wildcard rules, and each rule describes the boundary of each partition. And by doing that, we can easily describe this partition in the TCAM in the switches. And so all these authority switches together are actually hosting a distributed directory of rules. And it's not DHT because hashing doesn't work here. But here with a customized partition, we're able to like using TCAM hardware already existing in the switches to support this partition.
It's not an accident that all the dimensions are powers of 2, right?
Sorry?
You're just matching bits here?
Yes.
Yeah, so the fact that that's 2 and 4 is not an accident. You couldn't do 3 and 5.
Yes, so basically you need, this is kind of one rule, but in TCAM you need like several rules to describe this rule.
All right, now I get it. So you divide it up, and you just match the bits in the packet headers for a generic.
Yeah, it's like a traditional trick in TCAM. If you have a wildcard rule, how do you implement with power to boundaries? Yeah. Okay, so now we know that this partition information are just some partition rules we can install in all the switches. And what are these authority switches? They are just normal switches. They are just storing a different set of rules called authority rules. So in general, one switch can be both ingress switch and authority switch at the same time. So in general, one switch usually have 3 sets of rules in the TCAM. By storing these 3 sets of rules in the TCAM, we can easily support DFA. So the first set of rules are some cache rules that exist in the ingress switch and are reactively installed by the authority switches. And then the second set is some authority rules that exist in authority switches and are proactively installed by the controller. Finally, there are some partition rules that exist in all the switches and are proactively installed by the controller. And there are different priorities among these rules. So if a packet matches the cache rules, it can be processed directly, so cache rules have the highest priority. And the partition rules have the lowest priority, because if a packet doesn't match any of the cache rule or the authority rules, it will certainly match one of the partition rules. And with these partition rules, we can always keep the packets in the data plane. So we actually implement define with OpenFlow switches, and we don't need any change of the data plane, so we just store 3 sets of rules in the data plane. And then if a packet matches the authority rules, we will send a notification to the control plane. And in the control plane, we implemented the cache manager that sends some cache updates to the ingress switch. So at the ingress switch, if it receives some cache updates, it can change the cache rules accordingly. So we can see that the authority rules and the cache manager only exist in authority switches, and we just need software modification for authority switches to support define. So the next question is, how can we implement this cache manager? Yes?
Just from a security perspective now what's going on is that each authority switch has the ability to change the rules on every other switch in the network.
For its subsection.
Yes, so we assume that all the switches in the network are trusted and are controlled by a centralized controller. So we don't support any like malicious switches. Yeah. Okay, so the next question is, how can we implement this cache manager? The challenge here is there are like multi-dimensional flow space, and there may be wildcard rules in different dimensions. So here I'm still showing a simple example of 2-dimensional flow space. And here there are several rules. These rules are overlapping with each other, so they have different priorities. The rule 1 has highest priority, and then rule 2, then rule 3, then rule 4. So if a packet matches rule 3, we can't simply cache rule 3, because another packet that matches both rule 2 and rule 3 should take rule 2's action. So instead, the authority switch should generate a new rule that covers this blue rectangle space and only cache this new rule. A different case is that if a packet matches rule 1, then it can just cache rule 1 directly. So this kind of caching problem becomes even more challenging when we have multiple authority switches. So here in this figure, when we have 2 authority switches, each taken half of the flow space, then where do we store rule 1 and rule 3 and rule 4? So for example, for rule 1, if we store them in both authority switches, then these authority switches may make independent decisions on what they want to cache in the same ingress switch. So there may be cache conflicts. So instead of storing rule 1, we store 2 independent rules, and then store each of them in 1 authority switches. So we can see that we actually, with multiple authority switches, we actually increase the total number of rules in the whole flow space. So this brings a challenge to how do we partition this flow space so that we can minimize the total number of TCAM entries required in the whole switches. This problem is NP hard for the flow space that's 2-dimensional, even more dimensions. So we propose a new solution called decision tree-based rule partition algorithm. And the basic idea of this algorithm is cut B is better than cut A, because cut B follows the rule boundaries and doesn't generate any new rules. Okay, so there are other questions of how do we handle network dynamics, because the operators may change the policy at the centralized controller, the authority switch may fail, and the host may move to different places. And here I'm going to talk about how do we handle authority switch failure. So we actually duplicate the same part of flow space into 2 or 3 authority switches that are scattered in different places in the network. So this kind of duplication first helps to reduce the actual delay of redirection. For example, here we have 2 different switches, and for this ingress switch, it can choose the nearest authority switch to redirect the packet to. To implement that, we actually implement two different partition rules with the same flow space, but direct them to different authority switches. So in the normal case, for this ingress switch, the rule of the higher priority will take effect. That means the packets will get redirected to the nearer authority switch A1. Similarly, for another ingress switch, it will get redirect packets to its nearer authority switch. So if authority switch A1 fails, then we run OSPF protocols across the whole network, so the ingress switch can easily get these kind of switch failure events notification. And then this ingress switch can easily invalidate this partition rule, so that the secondary partition rule naturally take effect, and it can easily redirect the packets to the next nearer authority switch in the network. So in summary, by duplicating authority switches, we can reduce the actual delay of redirection, we can do better load balancing, and fast reaction to authority switch failures. So we actually evaluate our implementation of DFAN in a test bed of around 40 computers, and we implement two different solutions. The first is eSIM, and the second is DFAN. In eSIM setup, the packets will get redirected to the controller, and then the controller will install the rules so that the packets can get processed in the switch. But in DFAN architecture, the controller will pre-install the rules in the authority switch, so that when the packets can get redirected through the authority switch and get processed directly. So in order to be fair with eSIM, we only evaluate our prototype with a single authority switches. And also, since the key difference between the two architectures are the first packet of each flow, so we only count the first packet of each flow. And then we increase the number of ingress switches to test the throughput of the two systems. So here I'm showing the throughput evaluation. The x-axis is the sending rate, and the y-axis is the throughput. And both are in log scale. Question?
So your central hypothesis here, that like you started off with like wanting to make networks easy to manage, right?
Mm-hmm.
So in what sense has DFAN achieved that? It seems you only added more complexity on top of what ethane had.
So DFAN has the same level of ease management compared to eSIM, because operators only need to care about the centralized controller, only to say like whether this group of students have access to this group of servers, only need to consider all these high-level policies at the central place in the centralized controller. And then this is same with both architecture. And DFAN add an extra layer below this controller to make this policy enforcement more scalable. And operators don't need to worry about this.
Okay, so let me ask that. So you're essentially saying it's not like you made management easy. You made.
So how to scale management while still make it easy? Like today's network is totally distributed on all the switches. It's hard to manage, but it's pretty scalable. So we hope to find the right spots that achieve both easy to manage and also scalability.
And you don't, okay, just from a management perspective, you don't expect operators to pick which switches should be authority switches and things like that. They don't need to get involved in decisions at all.
No, operators don't need to worry about it. And we can just randomly pick a group of switches to do that. And with our partition algorithm, we can help operators decide with the amount of rules they want to install and the switch capabilities they have in the network, how many authority switches they need, how many partitions they need.
But is that because the worst case load on an authority switch in your architecture is similar to the worst case load in the ethane architecture? Because if switches are doing more, I would want like the better switches in my network to be picked as authority switches rather than some random small switch that connects to one computer get picked.
So if authorities wants to control like where to install the authority switches, they can certainly do that. certainly like input as a configuration.
I imagine the switches would be heterogeneous and operated. You would want operators to control it.
Yeah, but just specifying which ones are easier. I mean, I'm taking the question.
Yeah, the input of our partition algorithm is like different size of memory in different switches. And then we can like make sure the amount of rules we put in each switch can fit the TCAM size. And this is actually a good question. We have some ongoing work on like how can we eliminate this heterogeneity across the switches totally from the operators. So we hope that we have built a like virtual memory manager layer in the centralized controller that basically manage this kind of physical memory in different switches. And then the operators only need to have this virtual memory logic so that to write the operator's program and where they hope to install the rules. Yeah. Okay, so let's look at this throughput evaluation. Here I'm showing this figure about the sending rate and the throughput. Both are in log scale. So we found out that with just the one ingress switch, DFN already performs better than eSAN. This is because in the eSAN's architecture, the local ingress switch has a bottleneck of 20K flows. So the ingress switch can only like buffer the packets and send the packet to the centralized controller at the rate of 20K flows per second. Yes.
The y-axis is not really flows per second, right? Y-axis is flows that I have never seen before per second.
Yes. So it's like
how realistic is that?
You're right. Like it's the number of packets per second. First packet of each flow per second.
First packet of flow I have never seen before per second.
Yes.
So how realistic is this?
flows.
New flows.
Per
Yes.
second. So in our evaluation, we are only like sending new flows. Each new flow has like a single packet. So we basically eliminate all the following packets.
Well, okay. So how realistic is this in terms of workload? You looked at data center workloads. How often does this happen that you get 100K new flows at a switch per second?
I don't actually have real data on data center networks. I know like for web traffic, it's usually like 30 to 40 packets per flow.
But this is traffic internal to the data center, so web traffic is not an issue here.
Yeah. It's also like depends on how you define the flow. It's not like per 5 tuple is a flow. It's basically how fine-grained control you want to put for different flows. If you only want to have control on the source address, then like it's only about how many new source is coming to this switch. But if you want to have very fine-grained control on each applications, then it depends on like which application is sending the new flows.
Well, then the switch has to go do deep packet inspection, which is going to create its own delays.
So in today's OpenFlow, it supports like 10 tuples. So within these 10 tuples, you can.
And at what rate can it do that?
Sorry?
At what rate can it do 10 tuple inspection?
It's like normal switch today. OpenFlow doesn't add any hardware support today. So if a switch can process 1 gigabit packets per second, then it can still.
No, processing 1 gigabit packet per second is different than 1 gigabit per second new flows arising per second, correct?
Yes.
So that's your y-axis here. Your y-axis is not packets per second.
Yes.
The real y-axis is number of new flows per second.
Yes.
That's why it says flows per second.
No, it's new flows. It's
new flows per second.
Yeah. I'm just wondering whether you actually get those many new flows per second.
So it depends on the flow definition. So I don't actually have real trace on today's data center traffic, what kind of new flows per second each switch may get.
And so the difference between the two of them is primarily because you run out of buffer space for the packets in ethane? Is that what's going on?
The difference is this kind of switch need to have to do some software processing of buffer the packet and send the packet head to the controller. This is in the data in the control plane path, not the data plane path. So the control plane path throughput is only like 20K flows per second.
The character changes sharply. There's a knee in the curve. What is the bottleneck resource that you're hitting at the knee in the curve?
For the ingress switch, it's the CPU overhead, CPU bottleneck.
So, but you're generating almost the same amount of control plane traffic because in Difane, because you're still getting the
Yes, the
reactive.
key difference is we don't need to buffer the packets anymore.
So it is packet buffer.
Yes.
Okay.
Yes, sorry. Okay, so if we increase the number of ingress switches, then both systems could have better throughput, but the centralized controller in Ethernet can only handle 50K flows per second. And with Dfan, since we are doing everything in a fast data plane, we can achieve 800K flows per second with a single authority switch. And another benefit of Dfan is its self-scaling with the network growth. So if we hope to have support larger networks with high throughput, we can just install more authority switches in the network. So another evaluation is about how can we scale to the large amount of rules. So we actually collect the access control rule traces from one campus network and 3 different networks from AT&T. So for all these networks, we collect these access control rule data from all the switches and retrieve the network-wide view of what kind of policy operators hope to express.
That's good. This is an easier question. So suppose a packet goes through like 6 switches from host to host, and ethane rules are installed in the way how ethane works. Ethane rules will be installed on each of these 6 switches, right?
Ethane rules only installed in the ingress switch.
And the others would just forward?
It depends on what rule you mean. Like for these access control rules, it's only in the ingress switch.
Oh, I see. So, but for the second switch in that chain of 6, like it's a new flow for that switch, right?
Yes. So like for forwarding rules in Ethernet, like all the switches need to know how to forward the packets. So the centralized controller gets a new flow from the first ingress switch. It will tell all the switches to install the forwarding. It's kind of a small trick to speed it up. Yeah.
So you do the same?
For us, we use tunneling, so we don't have this issue.
But the tunneling only works for the first packet. But does the authority switch install the rules on all the 6 switches, or only?
So the tunneling also happens from the ingress switch to the egress switch. The direct tunnel between these 2 switches. So the forwarding rule in Dfan is only like the destination host what the egress router is, rather than what's the outgoing interface is.
Okay, maybe I want to take this offline, but you're not tunneling throughout. You're not tunneling all the packets, are you?
I'm tunneling all the packets.
Oh.
So you just have a VLAN tag saying
Yes.
clear. And from then on, everybody,
Yes.
all the other switches just clear route.
So the first packet in a flow gets a tunnel. It gets a tunnel label that takes it directly to the authority switch.
Yes.
And every subsequent packet in that flow gets a tunnel label that takes it directly to the egress switch.
Yes.
Is this what Ethan also does?
Ethernet does this kind of install forwarding rules in all the switches. It doesn't use tunneling. Yeah. Okay. So basically, for one evaluation we see is for this IPTV network we get from AT&T. It has about 3,000 switches and 5 million rules. And the amount of authority switches we need depends on the network size, the TCAM size, and the number of rules. But in general, we only need like 0.3% or 3% of the network switches to be authority switches. So in summary, let me use these slides to summarize what Dfan does. Basically, traditional networks are totally distributed, but it's hard to manage. And this new architecture comes from OpenFlow and Ethernet that's used a centralized, logically centralized controller, so it's easy to manage, but it's not scalable. And what Dfan hope is to pull back this trend a little bit so that we can, in Dfan, the controller is still in charge, so it's still easy to manage. But now the switches are hosting a distributed directory of rule, so it's more scalable. And when we talk to Cisco, Cisco is interested in this trend from traditional networks to DFIN because in their traditional network, they also have this kind of limited TCAM space in the routers that's not enough to install all the access control rules. So they view DFIN as a distributed way to handle large amount of echoes rules among a group of routers to address this limited memory in a single router.
So when you have a large number of authority switches, so if you have 3% of 3,000 switches, that's 90 authority switches. That's a fairly large thing. And if it turns out that the rules that you're having tend to go in both directions, then in general, the number of subrules that you're going to have to create is going to go up with the product of the number of authority switches and the number of rules, right? So now we're looking at hundreds of millions of subrules, which is going to cause you to eat TCAM memory faster than in ethane, which is going to cause cache misses to go up. How much of that?
So basically, you need a smart partition algorithm that can reduce the amount of rules. Basically, if there are so many overlapping rules in one area, you want not cut that area, but maintain that area in a single authority switch.
I mean, I guess I don't have a good feeling for what these rules look like, but my guess would be that.
So actually, for the AT&T's data, our algorithm works pretty well.
How localized are
the reason is that it's mostly access control rules that want to block, make sure the right set of customers have the right access to the servers. So basically, these customers are pretty independent. So there's not much overlapping among these rules.
Okay, so the rules don't tend to be block all traffic from a particular source or block all traffic to a particular destination.
Yeah, it's
they're
more
small.
independent. Yeah.
Okay, then you probably can't cut them off.
Yeah, but I agree with you that with more overlapping of rules, then it's much harder to break them apart. Yeah.
Well, in particular, if you have these star kinds of rules, let's say, if your rule set looked like half block destination, half block source, then no way you cut it is really going to help because they have these big cross-cutting rules, and the consequence of that is that as you try to scale this thing, you're going to eat up TCAM non-linearly.
Yes.
And
so for that, if you have an authority switch with larger TCAM memory size, then you only need to cut less. That would be help a lot.
Yeah, you might need to do something like that. Okay.
One small question: how are these rules invalidated at these switches? These policies?
For non-security rules, we rely on timeouts. For those rules that's really important, then you may need to remember them and proactively modify them as a cache system.
But if you have cache contention, you need to evict something from the cache. You've got this problem you pointed out earlier that the rules interact. Is it?
Yeah.
Always
so the worst case is all the
cache?
traffic goes through, always goes through the authority switches.
Is it always safe to evict a cache line, or are they sometimes interdependent from an ingress switch?
So for ethane work, when you evict it, then all the traffic needs to go through the controller. So there's a potential attack to the controller that if you send a lot of traffic, it will overload the controller. But in defense way, all the traffic will go through the authority switch. It's much harder to overload.
Well, I guess my question wasn't about the denial of service. It was that the rules have these funny interactions you showed where the rules overlap.
Yes.
And you described a technique for why it's safe to send a part of a rule to an ingress switch.
So
does that same property, does the way you cut up the rules have the property that it's always okay for an ingress switch to throw away a single rule? Or the rules, are they sometimes interdependent where throwing away one rule will...
Yes. So when we cache rule, make sure it's independent so that later when we evict it, it's fine. Yeah. Okay, so let me quickly talk about the second project, that is SNAP. How do we scale the performance diagnosis in data centers? So remember in DFIN, we achieve the scalability by resync the division of labor between the centralized controller and the switches. So now we are hoping to resync the division of labor between the network and the host so that we can achieve better scalability. So if we look at the search application in the data centers, a packet arrives at the front-end server. This front-end server actually distributes the packets, this request, layer by layer to a group of workers. And these workers will generate responses, and these responses could be aggregated layer by layer to the front-end server. So we can see that with just a single request from a single search application, it's already a lot of traffic in the data centers. And in fact, most of the servers are shared in the data centers. It runs on different storage, MapReduce jobs, and cloud applications. So it's really a very messy environment, even when everything works fine. So if something goes wrong, that the switch may fail, or the link may fail, or there may be some performance problem or bugs in the software component in these applications, it's really hard to identify. So it's actually a very challenging problem to how to diagnose performance problems for data centers. Because these applications usually involve hundreds of application components and runs on tens of thousands of servers. And another problem is there could be new performance problems coming out every day because developers keep changing their code to add new features or fix bugs. And there could be old performance problems coming out too because of some human factors. For those performance problems that we already know, developers without a networking background may not fully understand. For example, in networking, we have these detailed protocols like Nigel's algorithm, delayed ACK, silly window syndrome. It could be a mystery to those developers without a networking background. And for them to work with a network stack, it could be a disaster. So how does people do diagnosis in today's data centers? They first usually look at these application logs. It usually tells the number of requests you can process per second or the response time for each request. So developers could identify performance problems using these logs. They could find out that 1% of the requests have extra long delay, more than 200 millisecond delay. So since it's only happened for a small portion of the request, they may think that it's not their application code problem, but the network problem. So, but in the network side, we only have very coarse-grained switch logs that only tells the number of bytes or the number of packets each port can process per second in a switch. So in order to identify this, what really happened for these requests, these switch logs don't help much. Instead, the developers have to install very expensive packet sniffers and to capture large amount of packet traces. And then they want to filter out those traces that corresponds to this 1% request. And either manually use some tools to analyze these packet traces to find out what's really happened and find out the root cause for these problems. But most of the time we find out that the problem actually comes from not the application code, not the network side, but the interactions between the network and the applications. So we hope to build a tool that locates in the operating system layer, the network stack, and the end host, so that it can tell directly about the interactions between the applications and the network. So we don't want to use the application logs because it's too application specific. We don't want to use switch logs because it's too coarse-grained, and packet traces are too expensive to capture all the time. Instead, if we can build a generic tool that's lightweight enough to run always in the network stack layer in the end host, and is fine-grained enough to capture all the performance problems, then it would be great. So we actually build a tool called Snap, a scalable network application profiler that runs everywhere all the time in the data centers to capture the performance problems. So in Snap, basically the first step we do is that collect some performance network stack data from all the connections on all the end hosts. There are basically two types of stack data we collected. The first type are relatively easy to handle is some cumulative counters. So these counters are like the number of packet loss, the number of fast retransmissions and timeouts that each connection have experienced, or the round-trip time estimation that TCP used for congestion control, or the receiver end, what the amount of time the receiver window limited. For all these counters, we can easily reads them periodically and calculates the difference between two reads. The second type of data are some instantaneous snapshots. It's relatively harder to capture because if you read them periodically, you may miss some important values. So we use some Poisson sampling to make sure the snapshots we read are like statistically correct. These data are like the number of bytes in the send buffer, the congestion window size, the receiver window size, and so on. With the data we collected from the network stack, we hope to do the performance classifications. Yeah.
Today allow you to do TCP offloading on the NIC. Don't they provide these counters for you automatically?
Yes. The good thing is like Windows operating system already provide these counters, and we just need to read these counters.
I don't mean the network card, the NIC.
The NIC don't have this kind of per flow, this kind of TCP level information. It only has this packet information.
Even the ones that actually offload, they sort of, you can offload TCP.
TCP is never fully offloaded.
Well, whatever you uploaded, I mean, presumably the sample RTT, you would imagine that the NIC.
Yeah, RTT is easier to handle, but like other stack information, like how do you react to congestion control and what's the receiver window size on the other end? Yeah, it's harder to get. So we think that the stack information in the operating system layer is like only a small amount of information, but it's quite useful to tell you a lot.
I agree. I guess my question is, I know that parts of this stack information are being uploaded on the NIC, so the question would be sort of how much could NICs today help you with collecting this information without even involving the operating system, which presumably is probably quite busy doing other things.
Mm-hmm. That's interesting. So I think if you have a way to combine the NIC and the OS together, it will be certainly better. For example, one thing we don't really get here is like if the packet gets delayed, we don't really know if it's delayed in the NIC card or it's in the network. So if you have more information at that layer, it will certainly help here. Okay, so with this data we collected, we hope to do some classification, but it's a hard job because these performance problems may come from different application code, and we can't really classify all these root causes. So instead of classifying the root causes of the problems, we classify the problems based on the life of the data transfer. So here's an example that the packets usually start from the sender application through the send buffer to the network to the receiver, and then the receiver may acknowledge the data, the transfer of the data. And at each part, there may be some problems, like the send buffer may be too small, so it limits the throughput. The network part may have different types of packet loss events. And the receiver end, it may either not reading the data fast enough or not echoing the receive of the data fast enough. So luckily, we have already collected, with these counters we can easily tell the problems from different stages. For example, for the network, we already have the data about the number of fast retransmissions and the number of timeouts to tell this network problem directly. And at the receiver end, we already have the receiver window limit time and the round trip times estimation to tell the delayed ACK problem. And then we have the number of bytes in the send buffer to tell the send buffer problems. And if it's not the problem of all these other stages, then we classify it as the sender application problems. So we can find out that most of the problems we find can be directly measured using the stack data. And some relies on sampling and others relies on inference, so there's some error rate, and it's evaluated in the paper.
So is this classification going on in real time, or is the data being collected?
Yeah, one of our goals is to keep the classification simple enough so it can be done in real time. It can tell you directly about the problems for each connection in real time.
And is this done in the root VM or in the guest VM on in a data center node?
So if you have this kind of operating support in the guest VM, then you can understand it. Yeah, if you have the operating support there, operating system support there, then you can get it.
Ping is not virtualized.
Yeah. So after we get all this data and performance classification for all the connections on all the hosts, we collect this data to the centralized management system. And here, because as data center operators, they usually have the full knowledge of their data center, like the topology, the routing, and the mappings from connections to processes and applications. So using all these data, we can do some cross-connection correlations. So we can find out the shared application code or shared resources like the host, the link, or the switches that actually cause the correlated performance problems. So in summary, Snap has two parts. The first part is on each host, we have some online, lightweight processing and diagnosis piece of code. And we also have an offline cross-connection diagnosis part to identify these correlated problems. And we actually deployed Snap in the real world in one of Bing's data center. That data center has about 8,000 machines and 700 applications. So we ran Snap for a week and collected terabytes of data. And using this data, we're able to identify 15 major performance problems. And during this week, about 21% of applications have certain level of network performance problems at a certain time. And here's a summary of the performance result we've found. The first is that we find one application that has the set buffer performance problem for more than half of the time. It's because the developers does not set the set buffer large enough. And also there are about 6 applications that have lots of packet loss events at the network layer for more than half of the time. And there are about 8 applications that's not reading data fast enough at the receiver end. And the most interesting thing there is there are about 144 applications that are not echoing data fast enough. It's a delayed echo problem.
Is the analysis straightforward once you have the data? I mean, it is?
So the classification part is really straightforward. And it's our goal to keep it really simple so we can do it online. And then this kind of correlation part involves large amount of topology and routing information data and how to do.
Analysis for one TCP flow. I'm thinking back to all the work on trying to critical path analysis on TCP or bottleneck analysis.
So for one connection, most of the identification is really simple. Like it's actually compared to packet trace, people have developed a lot of techniques to infer from packet trace what kind of problem it is. But here, since you are getting the data directly, you can directly tell what the problem is.
Okay, and if there are multiple problems, do you have a sense of what the bottleneck is? Which one is a real one, or?
So basically, we look at the stage of the data transfer. And if for a connection, it's always throughput limited. So we want to know which stage is the cause of its throughput limitation. And if it's an application, that's a good sign for us because the application is not running fast enough to generate the data. But since we have these counters in the stack, so we know that which stage is causing this throughput limitation. Yeah.
It's unclear to me, how can you automatically decide when there's a bottleneck, it's a send buffer, it's a timeout, it's a fast retransmission. What will be your algorithm to automatically look at the log and decide, oh, this is because of timeouts?
You can do that.
You can do that.
Because you already have the counters about the number of timeouts, the number of packet loss. So using these counters, you can directly tell if this connection is limited or not. So the key trick is, since we're observing in the TCP stack layer, it's the stack layer who handle these kind of bottlenecks. Like if the receiver end is too slow, the stack need to send less. So the stack already have the information about whether the receiver is slow or not. Yeah.
So how does this information get represented to the application? So the application might can do.
So here we do some
What's the best way?
Basically, as a data center operator in Bing, they have the mappings from each connection to different processes and applications. They use information to basically deploy their applications, but we can use that information to do the mapping too, between connections to applications. So we can find out for one application what are the connections that are using this code.
Let's give us some time to finish up, and then we can have the questions towards the said. Yeah.
You have like 5 minutes of talk time.
Okay, yeah, I'm almost finishing. So basically, we find out delayed ACK is a very important problem in this data center. One example is that one application can only send like 5 records per second at some time and 1,000 records per second at other times. The reason is that if a data has like all number of packets, the receiver end may need to wait for 200 milliseconds before it sends the ACK. And if the sender is waiting for the ACK, it will significantly reduce its throughput. And delayed ACK was used in the internet environment to reduce the bandwidth usage and server interrupts. But in data center environment, we hope that people can disable it because today we have much higher bandwidth environment and more powerful servers in the data centers, and we no longer need this feature in data centers and because it's causing a lot of problems. And interestingly, when we talk with Google people, and they also find this delayed ACK problem in their data centers, but they find it out with the expensive packet sniffers installed on certain racks in the data center. So they don't have a sense of how common this problem is in the entire data center. So to summarize Snap, we use a delayed ACK example to summarize Snap. Basically, we first monitor at the right place. We monitor at the TCP stack layer, so we understand the networking application interactions, and we monitor at the end host, so it's more scalable and more lightweight. And also, we have algorithms to identify these performance problems for each connection. For example, how do we infer delayed ACK problems? And then we have some correlation algorithms that can find out problems that across connections. For example, we can identify those applications that have significant delayed ACK problems. Finally, we can fix we hope to work with operators and developers to fix these problems, like disabling delayed ACK in data centers. So in summary, we actually built 2 systems. The first system is called DFIN. It focuses on how to scalably configure devices to express the policies. And the second system is called Snap. It focuses on how to scalably collect measurement data and perform diagnosis on the end host. And for future work, I hope to continue working on this edge network area, but focuses on the interactions between the applications and the network and the platform. So the first aspect is how to make the platform to better support the applications, make it more flexible using software-defined networking techniques, and make it more secure by combining host and network defenses together. On the other hand, I want to look at how to make applications use the network better. I want to look at different new types of applications and see how to fit them better with these emergent types of networks, like the cloud home networks. So I have also done other researches in 2 main streams. The first is like how to support flexible network policies and how to build networks that support applications better. And I'm happy to talk about all these topics offline. So in summary, my research style is I hope to look at practically challenging problems and want to combine those new algorithms and data structures with real prototyping so that we can solve the problems in the internet and data center networks. Thank you.
I'll pass. I don't want to give it a hard time, otherwise I would have no questions asked.
You offended him now.
I'll ask you a question.
Go back to the slide where you listed both the different apps, the number of apps that had which problems.
Mm-hmm.
So yeah, this one. I must have missed what the 6 apps that are having a network problem. What is the network problem that you?
So all these problems are packet loss events. They just have different types of packet loss events. So we think that these applications may not be written in a good way, so that like incast kind of thing, they write some synchronized write at the same time, so it always causes packet loss.
All right.